So I'm JP Smets. I run a company called Nexedi. You can find at this URL all the content of this talk if you want to access it later. And you can email me or call me if you wish. So we are probably the largest free software publisher in Europe with nearly 15 million lines of code which R&D was made in Europe. About 10 enterprise software covering a similar feature set as Microsoft for Enterprise. We work mainly for enterprise looking for very flexible solutions that can be maintained during 10 to 15 years and provide some kind of resiliency. We are self-financed, profitable, we have no venture capitalist, and we don't put money in marketing. This is why probably you don't even know us. But you know maybe our customers, such as Mitsubishi, Sanef, Airbus, the Department of Transportation in Oregon, or the Central Bank of West Africa, even GKR in China. And so I'd like to say that Python 3 in 2017 is a fantastic language as long as you accept to run multiple threads on a single core, experience poor performance for your arithmetics, rewrite most of your legacy Python 2 code, and for those who wish to use a single language for everything, sadly to learn yet another language in addition to JavaScript. So I'd like to now demonstrate what I just explained. So I'm running actually Jupyter and Python 2 and 3 on my Android phone, thanks to a very nice application called Termux, T-E-R-M-U-X. It's quite convenient. And this is a shell to my Android phone. So you see it's running various things. And I'm running actually Jupyter. So I just started it. You can see there's a token. And this Jupyter is running on the phone. And there are two files, tserial. It's just a piece of code that does sleep. It sleeps a lot. That's good after you eat. And there's another piece of code which sleeps while it sleeps. So it sleeps in two threads, so it double sleeps. And one would consider probably that sleeping in a serial way should be twice longer than sleeping in parallel. So let's see what happens. So I take a look. I will run Python 2 on this little piece of code. And I will first do a serial sleep. Sleep, 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 sleep in a single thread. So that's a surprise. I think it's 8 seconds of sleep. Now I will try to sleep faster by sleeping in parallel. Like you see, it looks like this. You sleep, but you sleep with two threads that you start at the same time instead of sleeping and sleeping again. So let's see the result. Is it faster? It's a surprise again. It's a bit slower to sleep in parallel. Too bad. So the good news is Python 3 has solved this problem. But how it solved it, you might be surprised. So now let's sleep in parallel with Python 3. Was there a keynote about Python 3 being faster than Python 2? Not today? When is it?
No, not this time.
Too bad. OK, Sleeping in serial way with Python 3 is about twice as slow as with Python 2, 15 seconds. Let's see with parallel sleeping now. Oh, that's again a surprise. Ooh. Ooh la la. That's sleeping a lot. Wow. So I must say my phone must be in addition a bit sleeping too much, but the result is that Python 3 solves the problem of, let's say, running 2 threads sleeping being slower than running 1 by making actually 1 run slower than Python 2. So finally, we at least have the same speed between running a single thread or 2 threads. But globally, that's twice as slow as Python 2. So I just want to show you the version. Maybe you would think I'm using an old Python 3 version. I think 3.621 is not so bad, right? Okay. So big companies like Dropbox, for example, have dropped their effort to create a fast Python runtime called Piston. That was 6 months ago. And I'm moving everything to Go language. And I'm very sad because actually my company invested about 1.5 years in Piston. And Google, they created something like Grumpy, and they love to show these figures where you convert Python code to Go language, use the efficient runtime of Go to spread the code over multiple cores, and show then that by increasing the number of threads with Go runtime, you get nearly linear performance increase, whereas when doing the same with the C Python runtime, your performance is collapsing. And you can find many such kind of presentations or articles. That's why C Python 3 is great if you can accept to run multiple threads on a single core. Sadly, or happily, I don't know which of the two, there are fantastic reasons to stick to Python 3. And in my opinion, the best reason is the incredible NumPy environment with SciPy, scikit-learn, Panda, Jupyter. And these alone, for me, are good reason to choose Python over about any other language as soon as you develop business applications. Because if you think about any other language suitable for business application, none of them can provide you at the same time good analytics and good expressivity with reflexivity to build the kind of dynamic things we need for management. So we are not going to go away from Python in Nexedy. There's another reason, is like most of our code base is in Python 2.7. Our ERP, ERP5, our big data platform, wendelin, our edge computing platform, it's kind of distributed cloud. Also, we have a resilient networking system that bypasses the Chinese Great Firewall. Most of our code base is Python 2.7. And we did a bit of JavaScript. This laptop running now UOS runs a mix of everything. We can't just go away from Python. So we have to find a solution. So let's restart the talk in a positive way. Python 3 in 2017 is a fantastic language if one can accept to run multiple processes on multiple cores. And if one can accept to experience native performance and native threads thanks to Cython, something that JavaScript, Java, Go don't have. if one can accept to hack Python 3 runtime so that all Python 2 code runs without changing it. That's what I'll introduce to you next year. It's ongoing. Basically, it's very simple. It's based on recognizing that it was a big mistake to have strings and byte arrays being different. Splitting the two was a good idea scientifically in the 90s, but in the 20th century, everyone understood it was wrong, so we are going to fix it. And finally, it's a great language because you can integrate with JavaScript with things like transcript, or there are good ways, for example, to mix Go language and Python. And happily, multiprocessing is what we've been doing for 15 years with the RP5 at Nexedy. It works very well, it's scalable, it's reliable, it's clean, it's very efficient in terms of usage of cores, but it has only one issue. It's inefficient from memory point of view. And I'm going to show how one can do multiprocessing in Python while being very efficient from a memory point of view. So let's suppose, that's a bit the change compared to 15 years ago, that we have to manipulate a big array of 16 gigabyte. Usually business applications are handling 10 kilobyte, 1 kilobyte objects and running 16 processes, each of them having a 1 gigabyte RAM footprint, is not really an issue in modern hardware. However, running 16 processes, each of which having a 16 gigabyte memory footprint, becomes a kind of issue. And this is actually what big data is changing, because business applications no longer use only floats or strings or ints, but they also use big arrays. So we have this 16 gigabyte array that we want to process in parallel by running 4 different functions on the same data at the same time. If we could use threads, we would just allocate one big process in gray, taking the 4 cores of the CPU at the same time and accessing at the same time the single NumPy, or let's say the single array, stored in a single copy in RAM. But if we do that with Python, this is likely to happen. We are going to try to run 4 functions at the same time, but actually only one will be run, usually, on only one core, which is a bit disappointing. So computation will be 4 times too slow compared to a system that would be based on a, I would say, good threading model. So let's allocate processes. Okay, I've allocated 1, 2, 3 additional processes. Sadly, there's no more space. They can't load the array. So I can run 4 processes in parallel efficiently using cores, but only one at a time can access the big array. That's still annoying. So I have to purchase more RAM. Then I can do the same with 64 gigabyte of RAM as what any computer scientist would do with 16 if he was programming in C++. Now imagine with 16, 24, 48 cores, it's a real disaster. You just can't even purchase the kind of machines that are needed for that. So this is the trick that we kind of invented. Instead of loading the array in the cpython runtime memory space, we have the array managed directly by the operating system. And each Python process runs in a different user memory space and connects through some kind of trick to that single block of data handled by the operating system. Through that approach, we can actually fit 4 Python processes in the system memory, and the 4 Python processes can access at the same time the single copy of the big array that's managed by the operating system. So in a sense, we are kind of solving the problem of either poor memory management or poor threading management in cPython runtime by delegating all big block memory management to the operating system. So let's see a demo. So I'm connected here to a server through my 3G connection that has a bit unstable latency between 100 millisecond and 5 seconds. So please apologize for the delays. So I will first delete a few things. I hope it's deleted. Good. Then I will have a look at my system. So it's running a lot of things. It has 12 core. It costs 30 euro per month, so you can get 12 Xeon core for that price these days. And many things running. And so I will now show how I'm handling this problem. So the first step is that I have to install a library called wendelin.core. So I run pip install. Let's try. So I already prepared it, that's why it will be very fast, but maybe it will take you 30 seconds. So install this library. Then I have to import the wendelin various, let's say, primitives and numpy as np. Then what I do is that I open a database. For those who know, dbopen is a function of the ZODB database. Then nothing special. Then what I'm going to do now is to create an array, like an ND array, but managed by wendelin.core instead of being managed by traditional RAM manager in cPython. So root represents the root of the database. ZBigArray is a class that lets you create persistent arrays that are out of core. And transaction will actually flush data to the kind of database we just opened previously. So nothing. Then let's look at how the array looks like. It's an instance of the big array class. And now let's slice the array and look at the result. And this is a traditional NumPy array. We can double check that, numpy.ndArray. So we are just manipulating normal ND arrays. We can call any method, it works. And just to show you that it's a real ND array, we are going to play a bit with Cyton. So I've created a small Cyton function. Who doesn't know Cyton? Okay. Cyton, I would say, is a way to write C code with Python syntax. And if you do it in a clever way, it runs just as fast as writing C or C++. Then it's very easy to integrate with any Python program. So you write, for example, a function like this. It looks like Python, but there are a few types that are defined, and you can import it as a module. So you define a setup.py boilerplate, then there is a command to compile it, then you can import it as a module. So let's run, let's install Cython. Then we build the module that I just created. Done. We import the module, count even, this one. And we will find out that this count even module only accepts ND arrays. So if we pass a list, it will fail. If we pass the wrong shape, it will fail. If we call it with the right type, it will succeed. And we can apply this function count even to variable a, which is an ND array. So let's commit everything we've done. And I'm going to restart my Jupyter notebook now. Because with wendelin.core, actually what you get is at the same time persistency, better memory management, and out-of-core processing for ND arrays. You get the three at the same time for free. I could also add transactional memory or transactional computing. So I stop the Jupyter notebook that we were running and start it again. Okay. So just to prove, okay, it was stopped, connection failed. To make it, to be sure it reloads, I will maybe I need help. Okay. Maybe I need to do this. Okay. I will clear all output. So where were we? I think here. So first, I will re-import what I need. Then I will reopen the database that is handling the ND arrays. And I can find the same type of Z-big array as we created previously. If I slice it, I get again a normal array of the same type. So it's long because we have between 100 milliseconds and maybe 5 seconds due to the delay of the 3G connection. So now I'll show you that arrays can be made bigger and bigger and bigger without consuming so much RAM. So what I'll do is just add 4 times 1000 cross 1000, like a 10 megabyte block, and commit it. So it's adding, and what is sometimes interesting is to have a look at how memory is growing. So apparently, it's already done. So let's look at the shape. That's becoming a bigger array. Let's slice it. We can see everything works. So we are going to add now 100 times a 10 megabyte block to the existing array. And let's look at what happens. So what happens usually is when you modify data, you are consuming RAM until the transaction is committed. And after the transaction is committed, RAM will be garbage collected. So if you use the system to read a lot, you consume very little RAM in the cpython runtime. If you write a lot, you are going to consume a bit RAM. So in order to use the system, you have to make sure you don't do transactions that modify too much data at the same time. So I'm now growing at 274, it's reducing megabyte of memory footprint. The resident is the most interesting. It's keeping on growing. Because there's transaction commit each time. If I look here at the list of files, I should see this test.fs. Sadly, we don't have the size growing. So it's growing significantly. But the RAM is not growing so much. So still. Yes. Which one? Sur le... Okay, I show you. Memory size, so it's here. This one tells you that the resident memory used is 258. And you look at the process with Smets JP. This is the one that I'm currently using with PyParis. So I still didn't manage to make my Jupyter grow more than the other things running on the system. So this is done. We have now a much bigger array, as you can see. I think that's about a 1 gigabyte array. And we can call on it a mean. So it works. And let me see what happens on RAM. Oh, suddenly the RAM has become much bigger because we have loaded, sorry? Here, 8578. Can you see it? Yeah, because each block was read, but was not garbage collected because we have a lot of RAM still available on this machine. We have read the whole blocks to compute the mean. That's why the system loads them into RAM, and unless there is no need to flush it, it stays there. Then I can call on it my Cython function. Sorry. Yes, I should import it, of course. Here. Imported. And call it. And I will now close the database. So just to show you again, I will reopen the database and maybe even before that restart Jupyter because I'm still with a quite big memory footprint. So I turn off Jupyter, start it again, go back to the notebook, then I re-import wendelin.core, go a bit down where I open the database here. When I'm doing that, I'm actually opening an array that's pretty big. And if I look at the memory footprint, restart this. So it's so little. I've just opened an array and accessed an array of 1 gigabyte of RAM, at least. But I don't even see anything here in terms of resident memory. So I have a handle to that huge array. I can compute a mean, but as long as I don't access blocks in the array, no memory is used. Everything we are showing here could be done not only on a single machine, but on a cluster by installing something called Neopod. It's a distributed, transactional, replicated version of the ODB database. And so you can see it's already installed, and instead of doing dbopen with a file, you do dbopen to a URI to the database. Then you can have a cluster, all parts of the cluster sharing the same big arrays, and each Python runtime actually only accessing the big blocks of data through the handle. So with all these tricks, we have, for our use cases, solved the problem of memory management in a Python multiprocessing system. So now about the licensing. So we love GPL at Nexedy, so we decided we do GPL for everything. We have no objection to any other free software license. So we did GPL with a wide exception for any free software license or open source software license. So sometimes there are incompatibilities. We just wrote something to say we don't care incompatibilities. You can link our code to any free software. If you wish to do proprietary software based on our code, you have two options. One is to advertise us. Then you'll pay 100 euro per year. The other is to sponsor research. Maybe we ask 20,000 euro per year, then you are allowed not to advertise us. So we've done that because 20,000 euro per year is the price we are paying for a developer of MariaDB database that Google refused to hire. So we thought that's quite reasonable. So because we saw more and more of those big cloud companies refusing to sponsor the research of such important components as MariaDB or libraries, it's my decision now that our software will not be used to make proprietary systems without either advertising or sponsoring research. But for free software, we don't care. Thank you.